Okay, we're going to finish 3.1 because last time Ramin jinxed me and saying I wouldn't finish. So because of Ramin, we're still stuck on 3.1. There's nothing wrong with that. Of course there's lots wrong with that. Anyway, so we're going to pick up now. So I gave you a bunch of examples about, relative maximums and minimums, absolute maximums and minimums, and they didn't always exist, but there are cases where they will always exist. Which brings us to the next topic, the extreme value theorem. Which happens to be a very important theorem. There is a version of the proof of the fundamental theorem of calculus that uses the extreme value theorem. So it's a very important theorem, but it seems pretty simple. Basically it says if f is continuous, I wanted to mention that this is absolute. And absolute. Right, so basically, and I should mention, possibly afterwards, right? So this theorem is telling you that if your function is continuous on a closed interval, you're guaranteed to have an absolute max and min. We saw examples where we didn't have absolute max and min, and if you check those, what happened was the function wasn't continuous there, so you had like asymptotes or gaps. But if your function is continuous, you're guaranteed to be able to find these guys. So some graphical examples. Again. Dissect the target. So basically, once your function is actually continuous on the closed interval, you're guaranteed to be able to find an absolute max or an absolute min. So for example, here, your absolute max will occur here, the absolute min will occur here. And of course, there are local minimums and local maximums. Here, your absolute max. Here's the absolute max. Here's your absolute min. Here's your absolute max. Here's your absolute min. Remember, absolute max or min is just the highest y value that occurs. We call it absolute maximum min. And relative maximums and minimums is just a maximum or minimum in a certain region, right? So you sort of look for like a hill or a valley or things of a similar nature, right? But it's very important to know that if your function is continuous, that's a very important condition, you will always be guaranteed to have one of these. And we use this to our advantage many times. So another important theorem is Rolle's theorem. And this is sort of something that you needed to know on as the quiz part in the second test. If f means a local max or min at a point C and f prime of C exists, then f prime of C will be equal to 0. As long as your derivative exists, if you're at a local max or min, your derivative has to be 0. And we're going to use that later on. Notes. One important thing is that the derivative doesn't have to exist. If it exists, we know it has to be 0, but it actually doesn't have to exist, and we can use the age-old example, absolute value x. Right? So you think of y equals absolute value x, there's a minimum, there's a local min at x equals 0, but we happen to know that the derivative doesn't exist at 0. We've seen that before. The derivative limit did not match up. What else do you like? Also notes. Derivative can be 0. Example. Y equals x cubed at x equals 0 is an example. This one. So at x equals 0, you know y prime would be 3x squared evaluated at x equals 0, which is actually 0. But the derivative is 0, but it's not a maximum or a minimum at 0. Right? So this is another case where you have to be super specific. This is saying, knowing that a max or min is there already, you can get that the derivative is 0. It doesn't mean if the derivative is 0, you'll get a max or min. The order actually matters, right? If it didn't, I would have said it in the opposite order. It's very important to be specific. So this raises a very important question. We're often going to want to know when maximums and minimums occur, but the thing is, this tells us that it's possible to have them when we can't even find the derivative. And sometimes we know that when the derivative is 0, it still might not be a maximum or a minimum. So we're going to want to know when these occur, and this brings us to the notion of a critical point. Because seeing what max is or means. turns out if our maximum or minimum exists, it will happen at what we call a critical point. And that's what we're going to define here. A critical number C is a value such that f prime of C equals 0 or f prime of C is undefined. Right? Because we don't want to miss cases like in the case of absolute value. We want to know if the derivative is not defined, it's still somewhere we should be checking. Right? So wherever the derivative is 0, we should be checking according to Fermat's theorem, and sometimes when the derivative doesn't even exist, we should check there as well. We call these the critical numbers. Right? And the point C comma f of C is called a critical point. Just some vocabulary here. We're going to be using all this soon. Okay, so let's actually do some examples of that. Some examples for finding critical points. A equals x, B is actually value x, C is x cubed, D equals sin x. Let's restrict it to x is between 0 and 5. So the goal here is to find the critical points of the given functions. So let's begin. What do we do? Differentiate, right? The critical point is defined in terms of what happens to the derivative, if it's 0 or undefined. So here we're going to find y prime. This equals 1, right? So what does this mean? What are the critical points? No critical points. Right? Since y prime is not equal to 0 and nor is y prime undefined, right? It exists, but it's just never 0. So it can be a critical point. It fails at both criteria. Right? What about absolute value of x? At 0 is a critical point, because remember by definition this is just x if x is greater than or equal to 0 to minus x, if x is less than 0. This means that your derivative would be 1 in this case and minus 1 in this case. But that means y prime is undefined. The derivative doesn't really exist. At x equals 0, and here you can just check the limit. Right, the derivative limit doesn't exist. So this means x equals 0 is a critical value, which implies 0.0 is a critical point. Right, so the critical point ends up at the origin. C, if we have y equals x cubed, then y prime equals 3x squared. This is always defined.
Wait, why is y prime and b undefined?
We did this before. If you take the derivative limit, it goes from the right side will be 1, from the left side will be negative 1. So the limit doesn't exist. This is always defined. Why is it always defined? Because it's a polynomial. Right? So this is a polynomial, so it's never going to be undefined. However, if we set y prime equals 0, this means that x equals 0, which means that, again, here 0.0 is a critical point. Right? So you just find the derivative and you check both of these. Is it 0 or is it undefined? Right? What about sine x? Y prime would be cosine x. So set y prime equals 0. And of course, remember that cosine x is always defined. It's continuous everywhere. This means that your x value would be what?
Pi over 2 and b pi over 2.
Pi over 2 and 3 pi over 2. Well, I'm only between 0 and 2 pi over 2. So this means that what points are critical points? Pi over 2, comma. No.
Oh,
Original. We're going to talk about that in 3.3, right? The difference between coordinates and derivatives. You want to find a point on the graph, you look to the original graph. Right? So when x is pi over 2 in the original, what is the output? Sine of pi over 2.
1.
It's 1. Right? And sine of 3 pi over 2 is what?
Negative 1.
Minus 1. Right? Are critical points. What can you say about this point and that point? What do you notice with those?
The maximum, the second one is a minimum.
This is a maximum and this is a minimum.
Oh, yeah.
We're going to get back to that.
But can you tell us how to do it?
Huh?
Can we try it first?
Okay, sure. Yeah, try the rest of these.
So how did you get the values for the x again? How you got the pi over 2 and 3 pi over 2?
The derivative, cosine x, I set it equal to 0. Right? This would mean that cosine x equals 0. And I just know where cosine is 0. I remember the cosine graph. Right? It's 0 at pi over 2 and 3 pi over 2.
Okay.
So are pi over 2 equivalent to critical values?
They're critical numbers, they're called. And the points where they happen are called critical points.
So what's a critical value?
Huh?
So what's a critical value?
Usually when you use the word value, you're referring to the y coordinate. It's just a vocabulary thing. All right, so these two are called critical numbers, and the coordinates called critical points. Okay, so Renee wanted to do this one.
No, I can't do that one. That one's fine. I can do the next one. Because, okay, y prime is secant squared,
Sure.
and then I don't know the roots. I don't know, secant squared.
So what do you want to do? You want to see if it's 0 or undefined, right? So let's ask, if secant squared x equals 0, is secant squared ever equals 0? No, because that's 1 over cosine squared, right? So you have a fraction where the top is never 0, so the fraction cannot be 0, right? So this has no solution. So it's never 0. What about being undefined?
So I'm never doing y equals.
Right, again, this is just 1 over cosine. So wherever cosine is 0 would be undefined, right? This would mean it's undefined at x equals minus pi over 2 and pi over 2. Right? Those are where cosine is 0. Are critical numbers. This implies what's tangent of pi over 2? Can you even find that value? Points don't exist. They're asymptotes, right? Right? This is your tangent. This is at pi over 2 and minus pi over 2. So we don't really attain a max or a min there, but we had to have checked. Okay, Randy, how do you do this one?
So y prime is 4x squared minus 8x. And equals 0, the roots are 0, 2, and negative 2.
So always defined, so you don't even check where it's undefined. It's a polynomial. So we set y prime equals 0 for critical points. This means that 4x cubed minus 8x equals 0. You would factor out 4x. We get x squared minus 2 equals 0.
2 or
Right.
4?
So it's basically the point where
0, 1 is
the slope is 0 or undefined?
Yes. Critical points happen where the slope is either 0 or undefined.
What comes before?
Well, these are the critical numbers, but there are no critical points because the original graph doesn't exist at these 2 points. They're actually asymptotes. So technically they're critical numbers but no critical points because there is no y value. Which would be like those people next door and go hunt them down. Okay. All right. So what are the values here?
0, negative 1.
No.
How do you get 2?
No.
Negative radical 2 and radical 2.
Minus radical 2, positive radical 2.
Why are you doing it like that?
What do you want? Because that's like the answer. It's a square. It's a square. You didn't. It's a square.
You think that x plus 1 x minus 1?
No, like it won't work.
Yeah, 1 plus 1. Oh, it's 1 times 1.
Yeah. Okay.
You didn't know what he was doing.
So these are the critical numbers. When x is 0, this means y is 0. When x is plus or minus radical 2, what is the value? Both will give you the same because the powers are even. So the y value would be what? If you take radical 2 raised to the 4th, what do you get? You get 4 minus 4 times radical 2 squared, that's just 2. So that's minus 4 are critical points.
Wait, what did you do?
I plugged in these numbers into it to get the critical points.
But why?
To get the y value, yes. What about radical x? Y prime would be?
1/2.
Right? This is not equal to 0, so we can't check that. So y prime undefined if x equals 0, this means 0, 0 is a critical point. Is it a max or a min? Technically, by our definition, it's neither, because there's nothing on the left side. It's an absolute max or min if you want to put 0 as an endpoint. It could be an absolute minimum, but it can't be a relative minimum. This is absolute min if on an interval that the left endpoint is 0, right? So 0 with some y value. Yeah.
So if they don't give us the domain, that would be true. They don't have a absolute minimum.
No, it would still be an absolute minimum. Because on any given interval, including 0, that would be the smallest, right? If my interval was over here, then the absolute minimum would occur always at the left endpoint. Right? This is always getting bigger and bigger. So the leftmost endpoint will always be where the absolute minimum occurs. But technically, it doesn't have a relative minimum. We're going to wrap this up in a neat little package eventually, but this is just getting you the basics, right? So critical points are where the derivative is 0 or undefined, right? On the test, some people have got the derivative is 0, but they forgot to mention the derivative could be undefined. You have to check both conditions. Let's move on. We're going to do the closed interval method. And this is pretty much guaranteed to come on the final, so just learn the idea here. So here's the steps that we're going to take. Find f prime. First step. Second step is to find all critical points. 3. Find the values of f at each critical point and at the endpoints.
What do you mean by endpoints?
The endpoints of the interval at a and b. And the last step is to make your conclusion. The largest value from 3 is the absolute max. The smallest is the absolute minimum. So this is a step-by-step method for identifying the absolute max and min, especially if you can't bother to draw the graph and look at the picture. You can actually do it algebraically by doing this method. So let's do some examples here. Like I said, you're guaranteed to be asked some sort of question, find absolute max and min of this function on this interval. It'll always show up. It's a very important thing to know how to do. Okay, go. Do the first one. We actually did half the work for that one already. Yeah?
So y prime equals y cubed minus 8x.
For x cubed minus 8x, this means critical points.
0.
So for critical points, set y prime equals 0. This means we have 4x cubed minus 8x equals 0. And we actually solved for this already. So x was either 0, minus radical 2, or positive radical 2.
Now you substitute it into y.
Well,
Right.
To y.
So we go to find y of 0.
0.
Or b 0. We did this already. Y of minus radical 2.
Would be
But
4.
before doing this, we did this already. What else do we have to check?
Yeah, it's on the front. And then it's endpoints.
The endpoints.
Yeah.
What are the endpoints here? Here, your a would be minus 2. Your b would be 3. So we also have to check those values. So we're going to check y of 0. We're going to check y of minus radical 2. We're going to check y of positive radical 2. We're also going to check y of minus 2. We're going to check y of 3, right? So you check the value at all points that are in this interval, right? Is there anyone that we would exclude in this case? No, 0 is between minus 2 and 3, so is plus or minus radical 2. Minus 2 and 3, right? So there are times when they'll try to trick you, right? When you solve for the critical points, you might get someone that's not in the interval. You're not supposed to test it, right? But here, they're all here, and we can find the values. This was 0. I think we thought minus 4 for these. What was, if y is minus 2, what do we get? Well, just plug it in, right? 16 minus 2 squared is 4. That's also 16. We get 0. What about if y is 3?
45.
Huh?
45.
You're telling me the answer? Right, so that's what? 81 minus. Okay. So now, conclusion. Absolute max is what?
At 3.
Y equals 3, which is 45. you should state the answer like this. Give us, the value and the output, right? The whole value. Absolute min is
Plus or minus root 2.
right. Y at evaluate plus or minus root 2, which gives us minus 4. And that's it. So what's actually going on here? I think also last time we drew this function, we found the intercepts, which was 0 plus or minus 2, right? And it was like a W, right? Something like this. And we wanted to cut it off at minus 2, which is here. So we forget that. It starts here. And we want to cut it off at 3. So on this interval, this is telling you that absolute max happened here when you were at 45. Right? This is your absolute max. Your absolute min happened here, the lowest values, which we actually know this is at radical 2 comma minus 4 is an absolute min. This is at minus radical 2 comma minus 4, which was an absolute min. Right? So remember, last time we actually figured out that these guys are relative minimums and absolute minimums, but we actually didn't know the coordinate until now. With the power of the derivative, we could actually pinpoint exactly where it happens. Right? In pre-calc, you couldn't do that. Not with every curve. Right? So the derivative actually gives you the power to locate specifically and exactly where maximums and minimums occur. Right? So that's what's going on in this case. What about in the second case? This one's slightly harder to graph, so it'll take more work than I'm willing to do right now to actually draw the graph for that. So we're just going to know what the answer is without even knowing what the picture looks like. Okay, so how do we do that? Find the derivative. This is 2 cosine x plus 2 sine 2x by the chain rule, right? This is of course always defined, so we don't have to worry about undefined parts. So for critical points, set y prime equals 0. This means I'm 2 cosine x plus 2 sine 2x equals 0. How do I solve that?
Double out the formula?
Double out the formula. Now what?
Factor out 2 cosine x.
Factor out the 2 cosine x, we'd be left with 1 plus 2 sine x. So this means cosine x equals 0 or sine x equals minus 1/2. Now, what x values does this happen for in the range, in the domain 0 to pi? This happens at pi over 2 and 3 pi over 2. What happens here?
7, 5, 6. 7, 5, 6.
Is there only one point?
11, 5, 6.
7 pi over 6 and 11 pi over 6.
When you get 4 sine x cos x.
Double angle formula.
Oh.
Since sine 2x is actually equal to 2 sine x cosine x.
Okay.
You have to remember that stuff. I'm not going to be like the professor before this class and actually write those formulas on the board. I expect you to remember them.
we have to remember this for the final?
What?
Do we have to remember this for the final?
Yes, yes. You are going to be tested on things like that. Double angle formula, half angle formula, they'll expect you to know this. Covering identities, all that. Huh?
He's not a professor.
What? What? Oh, that would mean like you have something like a fraction where the denominator is 0, or you have a secant or something like that. Because you won't be able to plug in the value to your derivative. Right, so if you have something like y equals 1 over x, you know that the derivative is minus 1 over x squared. You can't plug in x equals 0. So x equals 0 would be a critical point. It actually doesn't exist in the original function. That's fine. Right. Might be. In this case, it's 9 because there's an asymptote. Right? There are cases where it could exist. For example, if I'm looking at y equals. In this case, minus 2 would be a critical point. But you have a whole graph. So it depends on the graph. Anyway, so now that we know this. Alright, so now that we know this, what do we do? What is A and B here? 0 to 2 pi. And now we're going to test all these values. So I need to know what is y of 0, what is y of 2 pi, what is y of 7 pi over 6, 11 pi over 6.
Professor, I have a question. How did you get on 7 pi and 11 pi over 6? You just put it with sine equal to -1/2 of the graph, right?
Yeah. So if you have something like sine, if you know sine x equals minus a half, basically what you do is you think of where is sine x equal to 1/2, right? The positive, right? That's going to give you the first quadrant, right? You know this happens when x is 6 from that table that I had you remember. So now what happens is you have this guy. You know that angle is 0, this angle is pi, right? Now if you're looking at for sine of pi over 6 means you take pi and you divide it into 6 pieces, right?
Yeah.
Now we know that all students take crack. So sine is negative where and where? In these two quadrants, right? The reference angle happens closest to the x-axis, right? So you know you have to get here, you have to get here. So how do you get here? Each pizza slice is pi over 6. How many pizza slices do you need to get here? 1, 2, 3, 4, 5, 6, 7. Right? And you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to get here. So now we have to find these values. If I plug in y of 0, sine of 0 is 0, cosine of 0 is 1, so this is just minus 1. Sine of 2 pi is 0, cosine of 4 pi is positive 1, so this is 1. What about pi over 2? Y of pi over 2? Y of pi over 2? Do we know what we're looking at?
Yeah.
That's y. What's y of pi over 2?
Yes,
Right, if you plug in the function, right? This is 2 sine pi over 2 minus cosine of pi, right?
Yeah.
What's sine of pi over 2? This is 1. Cosine of pi? Minus 1. So So this is just 2 plus 1, right? That's a 3. What about 3 pi over 2? This is sine of 3 pi over 2 minus cosine of 3 pi, right? What's sine of 3 pi over 2? Sine of 3 pi over 2.
Everybody's technical shot.
Yeah, suddenly everyone's shy now.
Radical 3.
Huh? It's negative 1. Sine or cosine is never radical of 3. Radical of 3 is bigger than 1. The maximum for sine is actually 1. Cosine of 3 pi.
3 pi over 6.
What are you
No, I plugged in 3 pi over 2 as cosine of 2x. The 2's cancel. I get 3 pi. Cosine of 3 pi? No.
No, it's 1.
No.
Negative 1. Negative 1.
It's minus 1.
Negative 1, I said.
So this is minus 2 plus 1.
Oh, yeah, it's minus 1 because it ends
2 sine of 7 pi over 6 minus cosine of 7 pi over 3. What's sine of 7 pi over 6?
That's a negative.
That's 1.
Negative a half.
Negative a half. We actually did it over here.
Yeah, negative half.
So this guy here is minus 1/2. What's cosine of 7 pi over 3?
Oh, that's easy.
It's negative.
Oh, that's.
It's,
No. It's 1/4. No.
Okay, so we want to figure out what's cosine of 7 pi over 3.
Positive 1/4.
Remember when you're doing these, you looked at the special angle, right? The pi over 3. So this says you take pi, you divide it into 3 equal pieces. Pi divided by 3. Do it on the bottom. And remember, all students take crap. And then what you do now is you count off 7 of these slices. Where would that make you end up? 1, 2, 3, 4, 5, 6, 7. You end up in the first quadrant, so you know the cosine gives you the positive value. So this is actually plus cosine of pi over 3, which that we should have memorized by now is a half.
Yeah.
Yes, this is pre-calc, 195, cos before this. So this is minus 1, this would be minus a half, so this is minus 3 over 2. What about 11 pi over 6? So this means you have 2 sine of 11 pi over 6 minus cosine of 11 pi over 3, right? So similar to here, we want 11 of them. So, you know, you go around, that's 6, 11 will bring you here, right? So here cosine is still positive, so it's still going to give us a positive a half in this case. What about the sine? It's still going to give us a negative a half. So it actually gives you the same values.
wait, isn't the circle thing, do you know what the positive or negative?
All students take, right? All are positive, sine is positive, tangent is positive, cosine is positive.
I never learned that.
Okay, so absolute max is what?
No, I don't.
What's the absolute max here?
3.
Y at pi over 2 equals 3. Absolute min.
11 power 6 and 7 power 6.
Right. Y of 11 pi over 6, which is the same as y of 7 pi over 6, equals minus 32. Okay, that would be the answer for this one. Yes. And if you could graph this function, you realize at these points is where you have the highest value and the lowest value. So we know this guy has 2 absolute minimums and 1 absolute maximum.
We got asked a question that like in the past, would you break that apart?
No, this would be one question. Huh?
No, I just want to say
That's all I wanted to do.
Sine 7 pi over 2, 7 pi over 7, negative 1 over 2.
Yes.
How do you end up with? Oh, yeah, okay.
Remember, you have sine of 7 pi over 6. You look at the special angle, that means pi over 6.
Yeah.
You take pi, divide it into 6 pieces. Then you count off 7 pieces, it brings you here. The sign is negative there. So then this is just minus sine pi over 6. So you get minus a half. Or you just count off how many pizza slices you need. Where you end up tells you if it's a positive or a negative. But the values stay the same.
Professor, earlier, why were you giving coordinates? Like, you were like giving x and y. Why were you doing that? Like earlier on.
Before, because I asked for critical points. When you ask for points, it means a coordinate. Right. If I ask for critical numbers, that just means the x value.
Alright.
3.2 Mean Value Theorem. I will not allow you to jinx me again. Now, this is a super important theorem. By far, most people who prove the fundamental theorem of calculus uses this one. I think your textbook tries to use the extreme value theorem, but most people use this one. They employ that theorem. And most calculus books often prove a more watered down version of this. Super important theorem. Used to prove both parts of FTC. That's fundamental theorem of calculus. Everyone abbreviates FTC. Okay. But first, there's a special case that we call Rolle's theorem. This says, suppose F fulfills the following conditions. On a B. 1, F is continuous. 2, it's continuous on the closed interval. F is differentiable, meaning the derivative exists on the open interval, which means the derivative might not exist at the endpoints, we don't care. 3, f of A equals f of B. Then here's the conclusion. You can make a conclusion about this. What is the conclusion? There exists a point such that what?
Such that f prime of whatever equals 0. F prime of c equals 0.
Right. There exists a point C. Where does it live?
Between A and B.
Between A and B, the open interval. Right. So it's strictly between A and B, such that f prime of C equals 0. So that's Rolle's theorem. Illustration, it means the following. You have a function on AB, it's continuous, right? And f of A and f of B happen to give you the same value. Right? Then once your function is continuous and differentiable, it doesn't matter what it does in here, it can do whatever. There has to be some point C at which the derivative is 0, meaning the slope of the tangent line is 0. Right? You have to have a horizontal tangent line existing somewhere between A and B. Right? That's what the theorem is saying. This is Rolle's theorem. Right? Once your two endpoints give you the same value, then somewhere in the middle, you have to have a horizontal tangent. There is no choice. It has to be there. Right? Provided those three conditions are fulfilled. Your function is continuous, it's differentiable, and the two endpoints are the same, you have to have a horizontal tangent line somewhere. It cannot be the case that you don't.
What about those y equals 2x? I mean,
Huh?
what about those y equals 2x? Like that.
Y equals 2x, what's your interval?
A and B, I guess. I don't know, like, I mean, wouldn't that just be a straight line and they could find a derivative from that?
Right, but your endpoints wouldn't be the same.
You wouldn't?
If you look at y equals 2x, right, then if you pick any A
Oh,
and B,
I meant like a horizontal line. I meant to say like that. I meant like,
for horizontal line is also true. If you say y equals 2 between any A and B,
but you can't differentiate.
then every point in between the slope is 0.
Oh, yeah.
It's actually true everywhere for horizontal.
Oh, alright.
You can't apply it to 2x because the endpoints would not be the same value. As long as your endpoints have the same y value, you have to be horizontal at some point. Right? Because either you stay constant, but once you sort of deviate from that constant, you have to come back down.
Yeah.
And when you make that turn at some point, you'll be a horizontal tangent. So,
You can erase that.
huh?
What if it's like a corner?
Look at it.
What if it's like a corner? It's like
Corner would fail this one.
and what it means
Right, so corners would not work because the differentiability would not work. So if you have this, sure, there's no point where there's a horizontal tangent line, but the derivative doesn't exist here. So part 2 fails. But that is, his question is actually a very important question. One of the ways to get a deeper understanding in math is whenever you get a definition, thinking about when the definition does not work is actually very instructive, right? So thinking about cases where, when would this not work? It's actually a good line of thinking.
So there's at least one horizontal.
At least, could be a more than one, but there's at least one. Okay, so more examples. So yeah, I did one with the horizontal line. Right? This is Rolle's theorem. Mean value theorem is more general. In the mean value theorem, you don't have to be the same endpoints. The mean value theorem won't care about that. And we're going to, I don't know if we'll get to it today. So this, right, so here, any C between A and B works. Here, many C's between A and B works. You can also have the case where like there's only one C value that works. This is A, this is B, this is F of A equals F of B. Then your C would happen here at that one point. Only one C works. So if at least one C must work. Conditions 1, 2, 3, 4. Right? So as long as your function is continuous, it's differentiable, and the endpoints give you the same y value, you're guaranteed at least one point where there's a horizontal tangent line. That fact is super important.
That's 1 point, that's 2 points, right?
Here you'd have several points, like this C, that C, this C, Pretty much everywhere you have a relative max or min would work.
But in the other one, there's only one.
In this, there's only one. In this one, there are infinitely many. In this example, there are 1, 2, 3, 4, 5, 6, 7, 8.
Question. A little but like the corners, is there any way to like determine when something's going to be a corner without having to graph?
Yes, knowing that the function is continuous, but the derivative does not exist, means there's a sharp corner.
Oh.
We're going to get to that in 3.4, I think. In 3.4, we're going to talk about situations like that. How to identify when something is a corner, or undefined, or just a max or min. Give an example. And we'll stop after this one, I think. Find a value C that satisfies the inclusion of Rolle's theorem for this function. F of x equals x cubed minus 3x squared plus 2x plus 2 on 0, 1. Find the C value that makes Rolle's theorem true for that function. And after that, we'll stop. It's possible for Rolle's theorem to show up on a final. If it does, more than likely it will be part A of a two-part question where they ask you Rolle's theorem in part A and probably the mean value theorem in part B. So, but mean value theorem is essential. Like, it's coming. Mean value theorem is coming. It's like I said, it's a super important theorem.
Can you give us a question, like a question that was asked using Rolle's theorem, like
Yeah, that would be an example of a question. That would be a typical question to ask. And there's something that is not said in the question, but you'd be expected to do it in a complete answer. And that is, you have to check that all the steps actually hold. Right? So first, check the hypotheses, as they're called. So one, f is continuous since it's a polynomial. In fact, it's continuous everywhere, not only on that interval, but everywhere. Right? Two, f is differentiable, not only in that interval, but everywhere. And again, because it's a polynomial, right? We can apply the power rule and find the derivative, and it will exist everywhere. Three, check the endpoints, right? If I say f of 0, what do I get? I get 2. If I check f of 1, what do I get? I get 1 minus 3 plus 2 plus 2. That also gives us 2. So f of 0 is equal to f of 1. Check, right? So all three conditions are fulfilled by this function on that interval. So we know there's a c such that the derivative is 0. How do we find that c? Huh? Find the derivative, say equal to 0, and solve for the value, right? Now f prime of x would be equal to what? 3x squared minus 6x plus 2. We want f prime of c equals 0. This means I want to find the value where 3c squared minus 6c plus 2 equals 0. Can I solve for that?
You didn't say go.
What? Yes, go. Find it. What is C? I'm waiting on you. C equals what? What is C? Do you know?
Yeah, the fact that the
That doesn't factor.
2/3.
So you have to use the quadratic formula, which is going to give you what? Minus b plus or minus the square root of b squared minus 4 times a times c. So you end up with 4 times 6, 24, all over 2 times a, which is 6.
So 6 plus or minus radical 12.
So radical 12 can be simplified to what? 2 radical 3. So this is 1 plus or minus radical 3 over 3, right? Or if you want 1 over radical 3. Now what can you tell me about that?
Radical 3 over 3 is equal to 1 over radical 3.
Yes? Okay, so what's the C value? This means C is 1 minus 1 over radical 3. Why didn't I take the plus? Because I need to be in that interval, right? If I take 1 plus a positive number, I get outside of the interval 0 to 1. That one doesn't work. How do I know this one works? Well, radical 3 is bigger than 1, which means this whole thing is less than 1. So I take 1 minus a value less than 1, I'll get some positive value between 0 and 1.
Wait, I don't get why you had 3 over 3 is 1 over 3.
Well, there are several ways you can do it. You can notice that 3 is just radical 3 squared. That's one way to notice it. You could also notice that 3, this is just 3 to the half over 3 to the 1. Subtract the powers. There are tons of ways you can see it. We'll stop there.